Good afternoon, everybody. Today, we're going to talk about problem number 2 on the day 1 of IOI 2021. The problem is key. The online judge, again, is on the OJ online judge. So let's look at the problem. The problem is basically like this. You have n rooms, from room is from room 0 and to room n-1. Inside each room, you have a key. For example, here you have a key of 1. You have the same key here. Here you have a different key. Then between zones, they are bidirectional paths. But if in order to go through the path, you have to have the key for that path. Right? So the key here is key C. So for example, in this path has key C of 2. And on this path, for example, you have key C of 1. Okay, so then if you're here, you can go from here to here, but you cannot go from here to here. So if once you have the key, you will keep the key, right? For example, if you are here, then you can go here. At here you have key 1, right? Now you have key 1 and key 2. Then you can go, let's say you have another one. Okay, let's say it's key of 1. Then you can go here. Now you have both key 1 and key 2. You can go here, you can go, now you have key 2 now. Now you can go here. Okay, so then the question is, if you start at any room, okay, you can reach, as I said, you can reach to some other rooms. What is the minimum number of rooms you can reach for each one? So if you start from here, right, as I said, if you start from here, you can actually reach 3 zones. Start from here, keys 2, you cannot go anywhere because those are key of 1. So you have 0 zone. You can reach, sorry, not 0. You can reach 1 zone, which is yourself, right? But you cannot reach more than that. Okay, start from here, you can go here, you can go here, so you can reach 3 zones. They want you to list the number, which rooms have the minimum value, right? In this case, is room 2, right? So you will write a function, right, which has what are the keys in each room, what's the connectivity, the edge, right, from U to B, and what is the key to open that edge path. Okay, and then the constraint is n, which is number of rooms, 3e5. m is number of edges, 3e5. We'll come back to this a little bit later, this is very important. So how do we do this? Very clearly, we can do float fill, right? We can easily do BFS to float from each room, right? That's very easy to do. So float from each room is complexity of n squared, right? Because for each room, you potentially have to go to each other room. So, however, so obviously you would think this doesn't work, but however, look at this condition, right? Will they see a bunch of issues, problems like this, right? This is basically have vertex of less equals 3e5, and you have edge less equals 3e5. What does that mean? So if you look at one case, one extreme, which is every edge is connected to every other edge. I mean, sorry, every zone is connected to every other zone, right? So if you have n room, then you have n square, I mean, n minus 1 square to be exact, edge, okay? But the n minus 1 edge has to be less equal 3e5, right? So O(n) square works, right? So O(n) square is in the 3e5 range, so that works, okay? So if you look at another extreme, the first extreme is I have maximum number of edge, right? The other extreme, let's say I have maximum number of room, right? Maximum number of vertex. If I have maximum number of vertex, every edge has to be connected to something, right? So that means every edge can only go, every room basically can only have one edge, right? So when you do float fill, yeah, you go through every room, but every room you only go to one edge, right? So in this case, it's going to be O(n), right? Which is still 3e5. So now you can see, and you can prove that if you have conditions in between, you still satisfy. So with those kind of constraints, both number of vertex and number of edge are less than 3e5. It is actually okay to do BFS. I think we solved problem like this before. Okay, so now we say we can do BFS. Okay, we can do BFS now. Now how we do BFS? It's actually pretty standard. The only difference is you need to know which key you have. But for the past, you don't have it. You don't throw it away, right? Because later on, you still can go there. Okay, so then you basically do the almost a standard, right? BFS. So you have a queue, right? You start from the the vertex. You're starting, right? So then if you are visiting, so you have to keep a list of the keys you have, right? In previous case, you start with 1. Then you need to, if there's a room, if there's edge, you're not visited. So let's say this, you have to keep the list of edge blocked. Okay, so you have to say for which key, right? So for in previous case, I have key 2, right? If I start from room 1, if we look at this, if I start from room 1, I have key 2, I can go from here to here, right? That's okay. So then, but I cannot go here from here. So that means for that key, let's say this is your edge. This is room 0, room 1, room 2, right? So let's say that's it. So you have to keep a list, right? So basically for my key 2, I have edge between 0 and 1. Those edge I have is being blocked. Because later on, when you go to the second room, right, when you put more in the queue, then you see, oh, now I have key 2 now. Now I have, okay, room, I can go from room to 0 to 1, right? So, so then I have to add 1 back into my queue. So that's the only trick you need to do. In addition to standard visited, right? You need to standard visited. You also need to keep number of rooms that you have not visited. It's been blocked, right? You have to have number of keys that you collect, right? So you have to have a number of keys, number of keys that you have to have number of edge, you have to have what room you visited, right? Then you have to have number of edge that is blocked. So every time you get a new key, okay, then you see, is this key in the key that is blocked? Yes. If it's in the key that is blocked, then you're going to say, oh, I'm going to enable those edge now because it's not blocked anymore, right? Which means every of those zones that was not previously able to visit, it become visited, right? Because now I have this key, so this room 0 become visited. That's basically a slight modification of the BFS. The couple of tricks we said this, yeah, own school works. The couple of tricks we should play here to improve the calculation, right? So if you think about for each new room, what I need to do. For each new room, I need to make visited 0, right? So that is O(n). How? But there's a trick here. So why every time I have to check it to 0? For each room, each room has a vertex number, right? Why don't I say for each time I go to a room, if I can go to other rooms, I assign them visited as that same vertex number, right? So then this is always new, right? Because every time you increase the room number, this is always new. So you don't have to set it back to 0 anymore, okay? Then the other thing is I need to clean this kind of like 2D matrix, right? Which is a vector, of int, right? 2D matrix. I should keep this list. I will keep this list, right? Which edge is blocked. So I only need to clean those, right, which are blocked, right? So I'll keep, this is my 2D matrix, okay? I will also, for this 1D, I will also keep a list, right? I will also keep a list of these keys that was blocked, and I can remove it once I collect it. Okay, so to actually each time I delete, I don't want to delete it because if I delete it, then I take over. So why don't I just make it? I can make it as set because set only take log n time, right, to find it. Okay, then what else? Every time I have to clean it, right? Every time I can clean a vector, right? I can do vector, int dot clear, right? But this itself take O(n) time. Instead of this, I should use swap. So let me just show you this, right? This note. So vector clear. Instead of using clear, you can use vector swap, right? So for example, you can do, if you have a vector, you can do vector clear. That's one way. Okay, but a better way is you can do a vector swap, right? A clean vector swap. So that is a faster way because clear is linear to the size, right? It's often the vector is actually a constant if you do swap. Okay, so if you do this swap, this this list, this is O of 1. This is a constant. Okay, so this is faster. So those are the tricks you should play. Okay. So use swap. Okay. The complexity is constant. Okay. So instead of using clear, those are the tricks will further help you improve the calculations. The last one trick you want to do is when you do this each zoom, instead of doing from zoom 1 to n, you should randomize it. You should randomize which zoom you want to visit first. The reason for that is if you sometimes, right, they will give you, if you have, let's say zoom 0, go to zoom 1, and zoom 0, go to zoom 2, zoom 0, go to zoom 3. Then you have zoom 1, go to zoom 2, zoom 1, go to zoom 3. Then every time you visit this, if you take the order, sometimes the problem was structured that if you do exactly the order, you will actually visit the maximum number of rooms. But if you randomize it, it will help you. Then the last thing is, remember, we want to have a minimum, right? We only care about the minimum. Which room will reach minimum number of rooms. So if I did one zone, if I have one zone, if I did one zone, if I do another room, the other room goes to the room that let's say this room let's say I start from this room, right? Okay, so let's say I can reach 3 rooms. Now I start from room 1. If room 1 can reach room 0, that means number of room 1 can visit should be more than room 0, right? If room 1 has not been visited. So then in that case, I don't need to, if room 1 is not there, in that case, I don't need to explore that room anymore, right? Because this is not going to be the minimum. anymore. As long as this is more than that, right? So then in that case, I should have another vector, right, which is keeping which room I already counted and how many I have counted, right? So basically, so let's say you should have another vector which is said count room, or should say visited a room already, right? If in your plot field that you reach a room that is already visited, then you should immediately return back. You don't want to continue to the plot field anymore because you know it's not your minimum anymore, right? So you can return, the count, you can make it infinite, right? So those are a couple of different things you can do to speed up. Don't clean visited. Instead of just keep increasing, and keep the list, the index, so that you will only clean the rows in that 2D, right? And using swap instead of using clean. Randomize the order of which room you want to visit, and return the plot field early. Okay. Those are the things you can do to speed up the process. So the example code is here, okay, which more or less implement the idea I described. Right. So you build up the edge, you build up which room has which keys, then you randomize. See, you randomize it. And every time you have not finished it, it's a room, means room not visited, you go visit it, and you find out how many room this room can visit, right? So this is the BFS, right? So you basically do the plot field. Right? If this is a new key, right? Every time you get a new key, you find if this new key is recorded in your 2D, right? If the new key is recorded in your 2D, and those edges you have not visited, you go visit it. But if it's already, the room already visited, then you can say, oh, I'm not the minimum, right? Then for each of the edge, right, you do the same thing, right? If you have the key, then you already have the key, then you go to that edge, then you find the next one, right? It's here. Right? If you have the key, you go to the next edge. If you don't have the key, you add it into your 2D matrix, right? So then you find your, then you get your minimum, right? So that's basically the, he actually did not do the, he did actually spend a little bit more time to do the clean up the visited. You can use my trick here, which is make it even fast, a little bit faster, slightly. So that's basically the solution for this problem. That is not difficult at all. It's just a simple float field with BFS. The only thing you need to be a little bit careful is to keep track which edge is being blocked, and then when you can release it, right? That's the only thing you need to do to modify the BFS. Then you use a bunch of standard tricks to make it a little bit faster. Okay, that's problem number 2 for day 1 of last year's IOI. Right? It's actually not difficult at all. So this week's homework is to implement to solve this problem, right? Then please read the next problem, which is park. Again, a hint: it's not that this one is not actually difficult either. So read this foundation park. Hint: this is basically a coloring problem. Okay. Try to solve this, and next week we will talk about the solution for fountain parks. Thank you, everybody. Have a good weekend.